You have stuff for me. Okay. I claimed last week if H is a subgroup of G, then the order of H divides the order of G. It's a great claim. How can I show this? Given the way we've been working things in this course, I want to try and do this from a strictly theoretical perspective. So if I want to show that I can break G up, divide, right? Divide means to group stuff together into subsets in there. And I claim they should all be the same size as the order of H, right? If you divide, you get a quotient. I want my remainder to be 0. So I should have order of G equals something times the order of H. If I can find a way to relate the pieces in G to H. H is a subgroup, it's a subset. What about the rest of the stuff? If I can chop that up into things that are also of the same size, then I've done my job. And I've got a way to relate all of those other parts of G to this subset H. If I do this, I have H as one of the sets. Then I have all these other sets. I'm going to call these other sets cosets. But in order to do this, I need to figure out how to make a partition. Wait a minute, that's a loaded word. Partitions go with what other things that we've been looking at all freaking semester? Chapter 9, discrete math. Chapter 0, this class. Yes, but more. I partition a set into these things. But what else can I use to make a partition? An equivalence relation. So if I can find an equivalence relation on G, then I can call the pieces in that partition formed by the equivalence relation. I can call those the cosets. Okay. I'm going to do a left equivalence. Because I'm in groups, I don't know if multiplying on the left is the same as multiplying on the right, so I'm going to do multiplication on the left. Here's my definition. Given a subgroup of G, we define the relationship which I will call tilde L. Two things are equivalent on the left. By saying that A is equivalent left to B if and only if A inverse B is in H. Now, A and B can be anything in the group. They might not be in H. I know when they are in H, that's a guarantee. I claim this is an equivalence relation. Okay, man. What do I need to show if something is an equivalence relation? What do I have to show about it? Okay? To show it's reflexive, I need to show that each element's related to itself. A is left related to A if and only if A inverse times A is in H. But what's A inverse A? The identity. Is the identity part of H? Why, Noah?
I don't really know how to describe it. I just have to look at it and see.
Okay, but there is a theorem somewhere that guarantees me that this should be in there. I'm glad you have an instinct because the instinct is correct, but I'd like to know why. In every subgroup, we needed to show three things. We needed to show closure. We inherited associativity, so we didn't have to show that one. But we needed to show that the identity was in there and then the inverses were in there. That's how we knew that the subgroup was also a group. The identity of my group must be an H because H is a subgroup. Check number one. It's reflexive. What's next? Symmetric. Suppose A is left related to B. I now want to show that B is left related to A. Wait a minute. A is left related to B. That means that A inverse B is in H. All right. I want to show that B is left related to A. How do I express that in terms of H? make this note off to the side so we can follow it a little bit later. B being left related to A means B inverse A is in H. Right now, I only know that A inverse B is in H. How do I get from A inverse B to B inverse H? B inverse A. Exploit that same theorem now.
H is a subgroup.
H is a subgroup, so H not only contains the identity, it contains inverses of things that are in it. A inverse B is in H. That means that A inverse B inverse is also in H. Because H is a subgroup. What happens when you do the inverse of a product? Linear people, you should have seen this there too.
Reverse the order.
It reverses the order. I take the inverse of each piece and I reverse the order. A inverse B, all inversed, is B inverse A inverse inverse, which is B inverse A. And I know that's in H, which means that B is left related to A. Sneaky mother, it worked. Reflexive, yes. Symmetric, yes. What's next? Transitive. Okay. Suppose that A is left related to B and B is left related to C. Wait a minute. If A is left related to B, then I know terms of H. That A inverse B is an H. What does this one tell me?
B inverse C is an H.
What do I want to end up with? A is related to B, and B is related to C. I want to show that A is related to C. A being related to C means what in terms of H?
B inverse C is an H.
So I need to get A inverse C. H is a subgroup. Subgroups are closed. If I take two things that I know are an H and I multiply them together, the result is still an H. Hey, wait a minute. What do you do here?
You switch them to parentheses.
I regroup. And then the B and the B inverse, poof. We're transitive. Oh, I should finish that out. Wait. Therefore, A is left related to C, which is what I wanted. It's reflexive, it's symmetric, it's transitive, it's an equivalence relation. Every equivalence relation makes a partition. I now have G divided into cells based on things that are related. So I want to know what those cells are. What are the cells created by this partition? Two things are in the same cell if and only if they are related. But wait a minute. If two things are related, then x inverse y is in H. Right? If x and y are in the same cell, then they're related, and that means that this is true. Well, that means that x inverse y is equal to little h, where little h is some element of capital H. That's an H, not a B. Let's make that clearer, H. Bad handwriting, strikes again, sorry. But that means that y looks like xh. So if I wanted to look at the set of elements in G so that they're left related to X, that's the set of things that look like X times H, where H is an element of capital H. X is on the left. Using left multiplication for this whole thing. X is on the left. I'm going to call this set XH. Because that's how you make it, right? You take everything in H and you multiply it by X. By the way, if I am working with groups where the operation is addition instead of multiplication, we often will write X plus H. Instead of X times H. Questions on how I built this coset? I promise I'm not pulling this out of my ass. You've seen this before. Ready for an example? Let's consider the integers. Mia, under addition, I'll specify. So, somebody pick a number for me. Okay. Consider 5z, all the multiples of 5. That is a cyclic subgroup because that is the subgroup of G generated by 5 under addition. Pick an element not in 5Z. We're going to call this our group H, our subgroup. Give me a number not in there.
6.
Okay? Because I'm in addition, I'm going to write it with this notation. I would write 6 plus H. Oh, wait a minute. What's the subgroup H look like? It's all the multiples of 5, right? So what's 6 plus H look like? Every one of those numbers, add 6. Wouldn't I get the same thing if instead of adding 6, I added 1?
Is it 1 to 6 or is it 1 to 7 in that line? I thought we were adding 6.
I added 6 to each of these.
Okay.
So
I see.
I add 6, I add 6, I add 6. Notice each of those numbers jumps by 5, right? Because they're these numbers with 6 added to them. But clearly, I could just as easily have added 1, or I could just as easily have added 11, or I could just as easily added minus 9. Any of those numbers would give me this same set. How many different sets can I get with this idea?
Like within this, or
Within Z5, within 5Z as H, how many other sets are available to me? How many total sets are available to me? I've got H, I've got this one. How many others? But notice that this is going to come up the same no matter which of these integers I add.
So then would you say like divided by 3 because there's three different possibilities there.
Oh, but I have infinite many possibilities, right?
So if you add 4 to it, then
I should get something else, right?
yeah.
I could use 4 then.
oh, so is there 4 sets?
Well, there are a total of more than 4.
Like 4 distinct, right? That won't repeat itself when you.
There are more than a total of 4.
I was going to say relatively prime, but I'm not sure.
I kind of like that idea. 5 is already prime, though, right?
Mm-hmm.
So all the numbers that aren't multiples of 5 are prime relative to it.
Are those the only ones that will generate the same?
No, I could use any number here from this set, and I would end up with this set. But it turns out that if I pick the smallest possible number, then I could think of this. And that would be something different. Why? And that would make all my numbers, no, it wouldn't make all my numbers even, adding, right? So I'm going to get -13, -8, -3, 2, 7, 12, 17, da 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 da.
Because you're adding a multiple of 5, like to that set, because like you can do 1 plus 11, then you add 5, 6 plus 11, add 5, 11 plus.
All of these numbers differ by some multiple of 5. All of these numbers differ by a multiple of 5. But the reason they all differ by a multiple of 5 is because all of these numbers differ by a multiple of 5.
like the number you're adding to it. Like you can take, if you just have h that's like 0 plus h, and then you have 1 plus h, then you add 5, and then that's 6 plus h.
That would be the same thing, right? 1 plus h and 6 plus h are the same thing.
Yeah.
So what are the different ones?
So would you have a different one for like 1 plus h, and then 2 plus h, and 3, and then 4, and then 3?
And then I would get back to where I was starting, right? So I'm going to get 1 plus h, 2 plus h, 3 plus h, 4 plus h. And as soon as I get to 5 plus h, I'm back to here. Wait a minute. Where the have I seen this before? Except these aren't subgroups. Only this one's a subgroup. Because this is generated by 5. But I can't pick a number and include 0 in any of these. Notice the only one of these sets that has the identity in it is H itself. That's the only one that's a subgroup. Everything else is a coset, not a subgroup. I didn't do it with 5 last time. The last time you saw this in another course, I did it with 4. Mod arithmetic. All of the numbers in this set, when you divide by 5, they have a remainder of 1. All of these, when you divide by 5, have a remainder of 2. All of these have a remainder of 3, and all of these have a remainder of 4. And all of those have a remainder of 0. When you said 0 plus h, my brain went, aha, we're getting there. It's the leftover bit. As a matter of fact, this is going to work no matter what integer you pick. The fact that we picked 5, because Ian said 5. I could have done this with 17, we'd be here a lot longer. This works in any group that I can find a subgroup in, no matter what that group is. On page 98 in the textbook, they do 3 instead of 5. But let's think about what happens if my group is not abelian. Where is my square? Here it is. Subgroups. Let's sit there, subgroups. I don't have one here. All right, then we'll do D3. D3, there's a table for D3. On page, where's my D3 table? Where's my dihedral group? Here it is. Wait a minute. Where's the frickin' dihedral group table? I ate the damn table. I've got to put more bookmarks in this damn book. Groups of permutations. D3. Here it is, page 80. Here's my table for D3. All right? I found it. I need this table. I'm going to pick a subgroup. I can use lots of different subgroups. So let's pick the subgroup created from the identity and the mirror that leaves 1 alone and switches 2 and 3. Remember, this is the symmetries of a triangle. Well then, what I can do is I can create from my table new cosets. Let me pick an element that's not listed here. I'm going to pick the rotation P. To do this, I do P times the identity and P times mu. So I go into here, and on my table, I say, hey, let's look. What's P times the identity? What's anything times the identity?
So
Good. So that's going to be just P. P times mu. I don't know that one off the top of my head. So I go back to the table and I go to the P row, and I go over to here and I get mu P squared. I'm going to write that down. Please notice I have now taken care of 4 of the 6 things that live in my group. 1, 2, 3, 4. I need something that's not listed. How about P squared? What's P squared times I? Great. What's P squared times mu?
I don't know.
But I can look at the table on page 80 and I can find out. P squared times mu is mu P. Now remember, the entire set D3 only consists of 6 things. And notice that all 6 of our things are listed either in the subgroup itself or in the cosets. Here's the original subgroup. Coset 1 consists of these 2. Coset 2 consists of these 2. I would not expect you to do this without the table in front of you at all, because it's a pain in the ass otherwise. But if I can do it for this group, I can do it for any group of permutations. It's just hard. Questions? How does this help me prove the thing I wanted to start today with? What was the theorem I wanted to start today with?
H is a subgroup of G, then the order of H divides the order of G.
And what we were thinking is that we could divide this up into a bunch of cells with my partition. And then that would show that it divided. There are 6 things in this group. What do you notice about all the cosets we created?
Order 2.
Which means they're all the same size. Even back up there, all those cosets are the same size. They're all countably infinite, so that's not very helpful, but they're all the same size. I claim that every coset must be the same size. The proof is 1 line long. I'm back in discrete class. How do I prove the 2 things have the same cardinalities?
Does that mean you're a bijection?
There's got to be a bijection, right? It's got to be a 1-to-1 and onto function. How did we define AH? That set.
Every element that's in A to multiply by A.
So let's define a function. That multiplies on the left by A. We're in a group. What do you know about that function? It's definitely onto, right? Why is it 1-to-1?
All the values map to corresponding value.
But that's the definition of being 1-to-1. Why do you know that's true?
Is it just because we're multiplying by a constant?
Almost.
You can't multiply 2 different things by the same constant and get the same answer.
Because back when we were first talking about groups, we talked about canceling in groups, right? We said that in a group, AX equals B has one and only one solution. So F must be 1-to-1. By definition, F is onto. It's 1-to-1, it's onto. It's a bijection, they're the same size. Check mark. Poof. If all of my cosets are all the same size, then it has to evenly divide the order of the group. There can't be anything left over, or there'd be a set that wasn't the same size. Lagrange's theorem. If H is in G and the order of G is not is finite, I'll write it that way, then the order of H divides the order of G. Ready for the proof? Let order of G equal N and order of H equal M. And let R be the number of cosets of H in G. By the way, that includes H itself. Then M times R must be equal to N, which implies that M divides N with no leftovers. Two frickin' lines. I'm dividing my whole group up into equally sized pieces. The number of pieces is my quotient. I'm done. Counting results, combinatorial proof, is a huge, very powerful tool in mathematics. Ready? Here is a result I can get by doing nothing more than counting. Every group whose order is prime must be cyclic. Why? Because of Lagrange's theorem. I can always make a subgroup from any element, right? So here's my proof. Let A be an element of G other than the identity. Then look at the subgroup generated by A. How many things live in it? I don't know. But whatever that number is, it must divide the order of G. But G is of prime order. What are the only things that divide a prime? And if this element is not the identity, then the subgroup generated by it must contain more than one thing, because it must contain A and the identity. And that means the only other option for the order of this group is the whole order. Since order of the subgroup generated by A is bigger than 1, we have the order of the subgroup generated by A is the same as the order of the whole group G, and that is exactly the definition of saying that A is generating G. G must be cyclic. Only divisors of a prime are 1 and the prime itself. Well, this can't be 1, so it's got to be the whole thing. If I give you a group of order 31, the only thing it can look like is Z31. It must be a cyclic group. 31 is prime. I'm done. Right there. No matter what group you give me, if it's got a prime number of things living in it, it's ZP. That's a huge statement. That's why working with Z5, Z7, Z11, those are easy. Numbers are all prime. Z8, Z4, we had multiple options because I could decompose my group. Prime can't. By the way, our definition for the order of an element of a group was the order of the cyclic subgroup it generated. The order of an element is the order of the subgroup generated by that element. But that's an order of a subgroup. It must divide the order of a group. And the order of every subgroup divides the order of every group.
That also in there, is it?
Yes, that's also an A. Sorry. Bad handwriting strikes a third time today. I proved this for finite groups. But one of our examples was an infinite group, right? The integers. There is another version of Lagrange's theorem that the proof is a little longer to do it for infinities because everything divides infinity. All right, so I really need to write this argument a little more carefully if I want to do infinite groups. But Lagrange's theorem does apply to infinite groups as well. I just don't want to do that crazy proof right now. Questions? Even when my group was infinite, I came up with a finite number of cosets, didn't I? When we did 5z, we came up with 5 cosets. When I did D3, I came up with 3 cosets, including the subgroup itself. If I count cosets, that's this R number up here, I need a name for that. That comes in handy. So, here's a definition. If H is a subgroup of G, the number of left cosets of H is called the index of H in G. And we write parentheses G colon H. When my group is finite, then the index is literally the order of the group divided by the order of the subgroup. Reese, you said, hey, look, each one of them has 2 things, right? There were only 6. 6 over 2 gives me 3. There must be 3 cosets. It doesn't work for infinities because infinity over infinity is an indeterminate form. L'Hopital's rule comes into play. We're not doing calculus today. But that means I can think of my subgroup diagrams. Okay, wait a minute. Subgroup diagrams. What's the subgroup diagram again? There's a picture. We did a bunch of them. It's a subgroup diagram.
It's not the same as a Cayley diagram, right?
Correct. The Cayley diagram told me how things acted within a group.
Right.
I'm looking at subsets within that group.
So like you start with your full group on top, and then you draw lines down to like each of its subgroups, and then if there's a subgroup within that one, then you just keep going.
It nested the subgroups one inside the other, and it showed me subgroups that weren't one inside the other on several different lines. We had this descending sort of picture of subgroups. Okay. But that means I can have subgroups within subgroups. Yes? So how do my cosets count up when I do that? So let's suppose I had some nested subgroups. I had H and K is in H and H is in G. So in my subgroup diagram, it would look like this. And there might be other things branching off in other directions, but I have at least that part. And the indices, H within G is finite, and K within H is finite. So if I break G up in cosets of H, there are a finite number of cosets. If I break H up in cosets of K, there's a finite number of cosets. Then I can jump over the middle level and go directly breaking up G in terms of K. And the number of cosets is going to be the product of the two numbers we came up with earlier. If you're counting cosets, and remember, counting results were big, then I can count layers down by just counting the in-between pieces. I promise there's a reason to do this, but this theorem isn't intuitively obvious why it would be useful. I promise that'll come up in a bit. Questions?
This is weird, man.
I agree. I agree. I did all of my work, all for the past hour, on the left. What if I did it on the right? What if instead of this entire process being left equivalence, we define tilde R on G by A is right related, I'll use a capital R, right related to B if and only if A, B inverse is in H. The inverse is on the right instead of on the left. This is still an equivalence relation. The same proof we did works exactly the same way. I don't even have to change anything except where the inverse is. Everything we did before is going to work exactly the same way, which means I get a new idea. And my cell, the set of things that are equivalent to A, looks different. Because I get it by multiplying H with A on the right. I get a right coset instead of a left coset. If my group is abelian, then multiplying on the left and multiplying on the right is the same. So if G is abelian, the left cosets and the right cosets are exactly the same. So I can just use the term coset. But if my group is not abelian, these could be different. All right, we did the example in D3, right? So let's go back to that table on page 80. And we'll do the right cosets. We were using that as our subgroup. And we used P and P squared, right? Go back into my notes and double check that that was what I actually used. Yes, here we go. I did PH and P squared H. So I'm going to do them on the other side. I'm going to do HP, which means I get to do I times P and mu times P. What's I times P? Oh, good. What's mu times P? I have the foggiest freaking idea. Out comes the table. Mu times P is mu P. HP squared is I times P squared, and then mu times P squared. But I times P squared is just P squared, and mu times P squared is mu P squared, which I get right from my table. At which point, I go back and I look. H times P, P times H, they're different. P squared H is P squared and mu P. HP squared is P squared and mu P squared. these two spots are reversed between the left cosets and the right cosets. They're different. Is it always that way? No. Is it often that way? Yes, but not always. Now, in our addition one, doesn't matter what order you add in, right? 14 plus 5 is the same as 5 plus 14. So it doesn't matter whether I do the adding on the left or adding on the right, those will be the same because that's an abelian group. Let me work in an abelian group we've worked in before. Three. Let's look at the subgroup generated by 3. What's the subgroup generated by 3 in C6? Great. Because Z6 is abelian, the left coset is the same as the right coset, so I'm just going to call them cosets. Pick a number that's not in that H. Add it. So I have 2 plus H, which consists of the elements 2 and 5. And I have 1 plus H, which consists of the elements 1 and 4. And that's everything. That's the whole thing. I'm doing addition, right? That's why I wrote plus there. But that's the operation by default in Z6. It's addition mod 6. I want you to make me the table for Z6. But I don't want you to put the numbers from 0 to 5 in order. I want you to put them in order by coset. I want your table for Z6 to go like this. Now, I'm going to cheat. You don't have to actually do this, because I already did it for you. So don't text it. So I'm going to save you a little bit of time. But if we were to do this, something interesting happens. Page 101 has this table. And it looks like this. Notice I've color-coded it. Everything that's in the uncolored boxes, the lightest box here, those are all 0s and 3s. Everything that's in the dark box, those are all 2s and 5s. And everything in the medium gray box, those are all 1s and 4s. I managed to divide up my table to align in these sorts of blocks that we see here. And these blocks, that looks like a familiar behavior. I've seen this table before.
trifold group or something like that.
But there are only three things there, right? Medium, light, and dark. Only three things in that pile. And there's only one group of size 3. That's Z3. If I made it 0, 1, and 2, this would behave just like Z3. My cosets behave like a group themselves. Whoa. But if I were to do the same thing for the table on page 80, which was the table for D3, I'm going to use the left cosets because the left cosets and the right cosets were different. I need to look at them differently. So here's the left coset, P and NP squared, right? And then here's P squared and NP. Those were the left ones. The right ones went the other way. But notice what's in this block. P squared and NP. But in this block, that's not one of my groups, is it? That's not a coset. That's got I and mu squared P and P. That's 4 things, and each coset only contains 2 things. I can't color code this table the way I could color code the table above it. What the?
That's not nice.
You're right, that's not nice. Why is it not nice? It's not nice because the cosets weren't nice. They weren't the same on the left as they were on the right. The fact that the left cosets and right cosets were different meant that this table didn't break out as nicely as the one above it did. The one above it was abelian. Of course the left cosets and the right cosets were the same. This one wasn't abelian. There was no guarantee. It turned out that the left and the right were different. I would really like to know when my cosets are going to do this nice job for me. When they're not. When can I guarantee that I'm going to be able to color code my cosets table into a group? When can't I? It turns out that the correct answer to this is based on the homomorphism property. But not just for any subgroup. Remember, we said that homomorphisms preserved subgroups. If you had a subgroup in G, when you took its image, that was a subgroup in G prime. When you had a subgroup in G prime, when you took its pre-image, that was a subgroup in G. But it turns out that I don't want to look at just any subgroup in G. The left cosets and the right cosets for the kernel of the homomorphism. What's the kernel of a homomorphism again?
Like one function equals 0.
Or
Yeah.
one or the identity or whatever, right? That's what maps to the identity. Moreover, two things that are ending up in the same coset if and only if they end up on the same spot. Remember, homomorphisms are not one-to-one necessarily. This is an if and only if statement here. This is actually a fairly direct proof. I'm not going to do it in the next 2 minutes, so I want you to read this one because I think it will help you understand some of the other problems we're going to do a little later. But where have I seen this before? I'm going to go back to matrices. Let's look at 2 by 2 matrices. The determinant takes a matrix and gives me a number, right? So if I look at the determinant on the set of invertible matrices, that means I'm leaving out 0. That means I'm using multiplication for an operation instead of addition. So I'm going to think of the map determinant, which maps from the set of invertible matrices, which are 2 by 2, to the non-zero real numbers. This group is under multiplication, this group is under multiplication. That's a homomorphism, because I know from the properties of the determinant that the determinant of AB is the determinant of A times the determinant of B. That's the homomorphism property at its basis. What's the identity in R star? One. And that means that the set of matrices whose determinant is 1 is the kernel of this homomorphism. And that's the subgroup that I can use. And as a matter of fact, the collection of matrices, when I do the blocks in the table, those matrices share the property that each block has the same determinant. All the matrices are determinant 2. They're not a group, but they're a coset. This turns out to be really powerful in, of all places, physics. When you look at 3 by 3 matrices, this same idea, you get something called the orthogonal group and the special orthogonal group, and those turn out to be of huge import in modern physics. By the way, this is a homomorphism. How can I make it an isomorphism? This map phi is only an isomorphism if it's 1-to-1, right? Well, then the only thing that's allowed to be in the kernel is one thing. And then all the cosets will be of size 1, and it'll be a 1-to-1 function. A homomorphism is an isomorphism if its kernel has only one thing. That's the corollary immediately below this theorem. I'm not going to bother to write it down in the text. Hope you have a wonderful weekend. I will see you all on Tuesday.